Welcome to the last session of Module 4. Here we talk about applications of Q meter. First application is measurement of low impedance. Second one is measurement of high impedance. So we try to measure the impedance of an unknown element using this Q meter. So coming to the measurement of low value of impedance, we have this arrangement here. We have an oscillator, a switch is connected across low impedance, and we have a standard coil represented by series combination of R and L, and we have the tuning capacitor, and two values have been shown, C1 and C2. One is initial value, the other one is final value. Voltage across the capacitor is EC, and voltage across the source, that is oscillator, is E, and we have the Q meter, which is practically a voltmeter, because we try to measure the voltage across the meter. Initially, the switch S will be closed. Once the switch S is closed, our low impedance element will be bypassed, so that we have only the standard coil and the capacitor and the source, which is called as tank circuit. So here the resonance will be achieved by varying capacitance C1. So if we see the source frequency of the oscillator will remain fixed, and capacitance will be varied, and resonance will be achieved, and the capacitance at which the resonance will be achieved is nothing but C1. So here in this particular case, XL is equal to XC1, and resonance frequency FR will be 1 over 2 pi root of LC1, and then quality factor will be XL by R or XC by R, and practically it will be EC divided by E. In the next case, switch S will be set to open. Low impedance also will appear in series with the coil. So when low impedance also appears in series with the coil, effective reactance in the tank circuit is going to change. So the reactance of unknown impedance will be XS. Q2 will be the new quality factor. C2 will be the new capacitance at which resonance will be tuned. R1 is resistance of the coil before opening the switch. R2 will be the new value of resistance including the low impedance. That is, effective resistance after the switch is opened is R2. Before opening the switch is R1. RS is the series resistance of the impedance. So at resonance, XL plus XS will be equal to XC2. So we have FR is equal to 1 over 2 pi root of LC2. That is, when the circuit is tuned to resonance in this particular condition, when switch is opened, XL plus XS will be equal to XC2. Now here, XS is nothing but given by XC2 minus XL. So that is given by 1 over omega C2 minus omega L, because XC is 1 by omega C. We already know that XL is equal to XC1. So once that is substituted, we get, in place of omega L, we will be writing 1 by omega C1. So 1 over omega C2 minus 1 over omega C1. So XS will be C1 minus C2 divided by omega C1 C2. So this is the effective reactance. Then also we try to find the value of RS. RS is given by R2 minus R1. We try to write the expression for R in terms of Q. We know that Q is nothing but equal to XC by R. So R will be XC2 by Q2, and R1 will be XC1 by Q1. And here in place of XC, I substitute 1 over omega C, so that we get 1 over omega C2 Q2 minus 1 over omega C1 Q1. So if you simplify, we get RS is equal to C1 Q1 minus C2 Q2 divided by omega C1 C2 Q1 Q2. Now here, as I told you, RS is nothing but series resistance of the impedance, and XS is the reactance of the unknown impedance. Unknown impedance is nothing but the low impedance that we have connected. So we have got the resistance and reactance of the unknown impedance that is being connected. If the circuit happens to be, if the unknown impedance whatever is being connected happens to be only resistive, then tuning capacitance will not change, because the resonance was already achieved earlier, independent of low impedance coil. Then C1 will be equal to C2. So RS we get Q1 minus Q2 by omega C1 Q1 Q2. If impedance happens to be inductive, then XS, the reactance, will be positive. So XS will be C1 minus C2 by omega C1 C2. And if we want to calculate the corresponding value of inductance, XS is nothing but omega LS. substitute that ls will be c1 minus c2 by omega square c1 c2. In case the impedance, the unknown impedance happens to be capacitively dominant, then xs will be negative. So xs will be same formula, c1 minus c2 by omega c1 c2. In place of xs, I go for omega cs to calculate the capacitance. So cs will be c1 c2 by c1 minus c2. So this is how we can measure low impedance using Q meter. Next we go for measurement of high impedance of an unknown coil using Q meter. The arrangement is quite different here. We have the high impedance element XP in parallel with RP, and a switch is connected in series for this combination as shown here. As usual, we have the Q meter as well as tuning capacitor, oscillator and standard coil. So here again, initially the switch S is open and resonance is achieved. If the switch S is open, uh, the high impedance coil will not be there in the circuit, and circuit will just have your standard coil RL and then effective capacitor, Q meter and then oscillator. At that state, resonance will be achieved and the resonating capacitance value will be C1. So XL will be equal to XC1 at resonance. Then the switch is closed and then resonance is achieved. If the switch is basically closed, then this high impedance element also will be included in the circuit. Then resonance will be achieved. So at resonance condition, we know that effective inductive reactance will be equal to capacitive reactance. Total effective capacitive reactance is nothing but parallel combination of RP and XP. So XC2 parallel to XP, that can be written as XC2 XP by XC2 plus XP. We know XL is nothing but equal to XC1 during the resonance. So we'll substitute for XC1 in place of XL. So XC1 will be equal to XC2 XP divided by XC2 plus XP. Cross multiply and simplify. We get the expression for XP as XC1 XC2 by XC2 minus XC1. Try to express in terms of capacitance. We have XP will be equal to 1 over omega into C1 minus C2. This will be the value of reactance of the high impedance coil. Similarly, to what we have done in the earlier case, our intention is to find whether it is inductive or capacitive. If it is inductive, omega LP will be equal to XP. So LP will be 1 over omega square C1 minus C2, because already XP we have got it as 1 over omega into C1 minus C2. In place of XP, we go for omega LP and get an expression for LP. Or if it is capacitive, XP will be 1 over omega CP. So 1 over omega CP will be equal to 1 over omega C1 minus C2. So CP will be C1 minus C2. So this finishes the measurement of inductance and capacitance of the high impedance coil. So with this content, I conclude module number 4.